This is Chapter 10, Reaction Rates and Chemical Equilibrium. Section 1 is Rates of Reaction. Until now, we've talked about how matter is involved in chemical reactions and a little bit about how energy plays a role in those chemical reactions. Now we're going to move on to discuss the rates of chemical reactions, or the speed that a reaction takes place at. And we can see that the rates vary very much for different chemical reactions. There are three different examples given here. In the first, you have bananas spoiling, right? If you leave a banana or a piece of fruit out on your counter, over several days, it'll react with oxygen in the atmosphere and it'll spoil. It'll turn bad. And then the second example, you have a silver teapot, and if you leave that out for several months, it'll react with sulfur impurities in the air and it'll form this black tarnish on the surface. And then in the last example, we have carbon or graphite, which over the course of more or less 1 billion years can be compressed and pressurized and turned into diamond. Okay? This is sort of a chemical reaction. It's a rearrangement of the bonds and the relationship between the carbon atoms. They're both pure carbon, but they're different forms of carbon. They're different ways for the carbon to arrange itself. And so that process, again, takes around 1 billion years, more or less. So you can see there's a very large difference in scales for how fast a chemical reaction can be. In order to talk about what factors play a role in speeding up or slowing down a reaction, it helps to understand what factors are necessary for a chemical reaction to occur. So on an atomic or molecular scale, there are three conditions for a reaction to occur. The first is that you have to have a collision. Okay? The reactant molecules actually have to come into contact or come near one another. The second is that they have to have sufficient energy so that you break bonds in the reactants in order to rearrange them into the products. Okay? Even if there are no bonds per se in the reactants, there may be other ways that it interacts with the environment and other energy factors to consider. So you need a certain amount of energy in the collision in order for it to form the product. And then the third factor is the orientation. If you have molecules that collide with a lot of energy, but they're not oriented the right way for the product molecules to form, they're not going to form, and you're not going to have a reaction from that. So here we can see illustrations of these three, right? We're showing collisions, and the collision, this first one, forms a product because it's done with a lot of energy. This one, there's no product form because the collision has insufficient energy. So they do hit one another, but not with enough energy to break the bonds between the nitrogen atoms and the oxygen atoms. Okay? So this bond isn't broken, which means at the end they basically just bounce off of one another without reacting. Okay? And then the last part is the orientation. Okay, so here we see two different ways that the orientation may not be correct for the nitrogen to line up with the oxygen, right? To get a compound nitrogen monoxide, we need one nitrogen atom to be next to one oxygen atom. So here we have these two next to each other, but this nitrogen is not going to be able to attach to this oxygen. And here, maybe this oxygen could attach to either one of these, but this oxygen is not going to attach to either of them. So these are not in the correct orientation, and again, they're just going to bounce off, and you're going to be left with the reactants, the separate nitrogen and oxygen molecules. So this is an illustration of how all three factors are necessary for a reaction to occur. We can also understand these factors in terms of the reaction diagram that we've seen before. We discussed also the activation energy in the last chapter, and the activation energy is really the minimum energy that you need to put into your reactants in order to break all the bonds and begin to rearrange them so that they can then go on to convert into the products. Okay? So you have some energy in the configuration of atoms that represents your reactants, and you need to bring them to this state at the top here. This is a transition state. Okay? So every point on this curve really represents an arrangement of atoms somewhere along the line between the reactants and the products. Okay? So at the very top, you have the arrangement that corresponds to the sort of highest energy point in the natural progression from reactant to product. Okay? So you need to put in at least this much energy, the activation energy here, to bring you from the energy of the reactants all the way up to the energy of the transition state, and then you can go back down and continue on to form the products. But you have to put at least this much energy in to begin with. Okay? So this is one reason why you have a minimum amount of energy needed for a collision. Okay? But then it also is pertinent to the orientation factor as well, because you can see here this transition state corresponds to an actual physical arrangement of atoms. If they collide in a different way, then that transition state is going to be a little bit different. And if the orientation is too askew or not in a way that's conducive to the reaction, then the energy of that transition state corresponding to that is going to be way too high, and you're not going to have the energy to overcome it. So this activation energy, it's the highest point on this curve, but in some sense it's the lowest energy potential pathway from reactants to products. Okay, so that corresponds to the orientation that's sort of halfway between. So how do we measure the rate of a reaction? Well, the rate of the reaction is defined as the amount of reactant used up in a given amount of time, or correspondingly the amount of product formed in a given period of time. So you can use either definition to calculate the rate, and as long as you keep the proper ratio between reactants and products in mind, then you will always get the same answer for the numerical rate. Okay, so we see here the formula: the rate of the reaction equals the change in concentration of reactant or product divided by the change in time. Okay, generally, if you have the change in reactant, there'll be a negative sign because the reactant is being used up, and if you have a change in product, you'll have a positive sign because the product is being created. But that's not really something you need to worry about too much. This equation is not actually used all that frequently to actually calculate the rates. And in this class, we're not going to use this particular equation at all, really, to calculate the rates. So you just have to understand that it's talking about a rate of change, okay? Similar to how speed is a change in distance divided by a change in time. This is a change in concentration divided by a change in time. Now that we know what conditions are necessary for a reaction to occur, we can begin to talk about which factors will affect the speed or the rate of a reaction. The three most common factors that are usually discussed are the concentration, the temperature, and the presence of a catalyst in a reaction. We'll see in the next few slides how these factors actually relate back to the factors that are necessary for a reaction to occur at all. But we can also think about all of these factors in terms of that reaction diagram and the activation energy. And so a general rule is that reactions with low activation energies generally go faster than reactions with high activation energies. The reason is that a particle needs to get energy to get over that barrier represented by the activation energy. And so the lower that barrier is, the higher the percentage of molecules in a regular sample will have the necessary energy to do that. And so all of these factors that we're going to see will affect the rate, but many of them do it by affecting the activation energy or by affecting the way the energy that the system has relative to the activation energy. But first, we'll talk about the simplest one, which is the concentration. So we saw that in order for a reaction to occur, the first condition is that there has to be a collision between the reactant molecules. So for instance, here we have this blue atom and this orange atom, and if they collide and stick together and form a new bond, they'll create this blue and orange molecule. Okay, this is what happens when there's a collision, when there's a reaction. So if you have a certain amount of the blue molecules and the orange molecules in a container in a reaction vessel, then in a given period of time or in a given space, there'll be some probability of a collision occurring, right? And we can say, just define that, say that has a probability of 1. Okay? So then if we increase the concentration of one of the reactants, say we double the amount of blue reactant that we have, now there's twice as many blue particles in that region of space or time, and so there's twice the probability of a collision occurring with the orange molecule. Okay? If we double both of them, so we have twice as much blue and twice as much orange, then we've doubled both, and so the 2 times 2 gives you a 4-fold increase in the potential collisions. Okay, so it's a 4 times the probability of a collision occurring. So increasing the concentration of reactants increases the likelihood of a collision. Okay, so this is the way that it makes a reaction go faster. The temperature corresponds to the energy of the system. Okay, we saw, for instance, in a gas, the Kelvin temperature is directly proportional to the internal energy of the gas particles. That's true for most systems. The temperature is some measure of the average energy of the particles. So at higher temperatures, the particles have a higher average energy. They have more kinetic energy. That means they're going to move faster, they're going to collide more frequently, And each collision is going to have more energy, or it's likely to have more energy at least. So this means that a higher percentage of your reactants will collide with enough energy to make it over that activation energy barrier. Okay, so you can see how this is related to the activation energy. Eventually, you can heat it up so much that most of the reactants have the energy to get over, and then the reaction will be very quick. Okay, so the rule of thumb, it's not always true, but the rule of thumb is that for every 10 degrees Celsius that you increase the temperature, the reaction rate approximately doubles. And the last factor that affects the speed of a reaction is the presence of a catalyst. And this is actually related to the orientation criteria that we saw for a reaction to occur at the beginning. So remember, we said if the reactant molecules collide but they don't have the proper orientation, or they're not in the correct arrangement, they won't be able to rearrange and form the products. Okay, so the way this works is you have the reaction diagram, right? You start with the reactant configuration with a certain energy, and then the normal reaction pathway would be to take this sort of blue-green pathway up to the very top, that transition state, and then go back down and form the products. Okay, and so again, remember, this peak here represents some transition state along the pathway from reactants to products, and it has a certain energy. That configuration of atoms has a certain energy that you can calculate. The way a catalyst works is to lower that energy so that the catalyzed pathway would be this purple path up to only this transition state, and then back down to the products. So the way that it does this, there's two possible ways really for this catalyst to lower the activation energy. One way is for it to simply make the energy of that configuration more stable and lower, right? The energy is partially due to how the transition state interacts with this environment. And so the catalyst can change the environment and hold it in a certain position that's more favorable, and thereby lower the energy of that transition state. The other way that it can do it is to provide a totally different transition state, an alternate pathway for the atoms to rearrange themselves that has a lower energy transition. Okay? Either way, the net result is to lower the activation energy. So now there is less of a barrier, less of a hill to go over in order to get from the reactants to the products. Okay? So however it does its thing, the catalyst lowers the activation energy, and that increases the rate of a reaction. Okay? So a catalyst always increases the rate of a reaction, always speeds up a reaction. But keep in mind that the nature of the reactants is not changed, and the nature of the products is not changed. Their energy is the same, their configuration is the same. The catalyst is not combined with the reactants. It doesn't form bonds with the reactants or the products. So it doesn't really take part in the reaction except to change the energy of this transition state, which means everything else about the reaction is the same. The delta H for the reaction is the same, right? The difference between the product energy and the reactant energy, that's delta H, that stays the same. The formulas for the reactants and the product stays the same. The equilibrium, if there is one, between the reactants and the product stays the same. So the catalyst won't shift the equilibrium one way or another. So everything else about the reaction is exactly the same, but it's sped up, it's going faster. Okay? And this is because you've lowered the activation energy barrier. Here's just a quick summary of those factors that affect the rate of a reaction, and a sort of brief explanation for each of them, which is more or less all you need to know about each of these, right? As long as you understand how these work in practice, then this table is plenty for you to remember. So let's put this into practice. Okay, indicate the effect of each factor listed on the rate of this reaction as increases, decreases, or no change. So here you have 2 moles of carbon monoxide combining with 1 mole of oxygen to produce 2 moles of carbon dioxide. So if we take this reaction and we raise the temperature, is the reaction going to speed up or slow down, or not change at all? Well, the temperature is a factor that affects the rate, and if we increase the temperature, we have more particles that are able to get over the activation energy barrier, and so this is going to increase the rate of the reaction. If we remove some O2, we can see here O2 is a reactant. So if we remove O2, we reduce the concentration of O2, then this is going to decrease the rate. Okay? Remember, the rate is related to the concentration. So by removing oxygen, we're decreasing the concentration, which will slow the reaction down. In the most extreme case, we would remove all of the oxygen and then the reaction would stop. right? A rate of 0 means no reaction. So if you're not sure, you can think about it in that terms. What would happen at the extreme case where I got rid of all of the oxygen? And then C is adding a catalyst. We know adding a catalyst is always going to increase the rate of a reaction. Okay, that's just what a catalyst does. And then the last one is lowering the temperature, right? So in the first one, we raised the temperature and it increased. So lowering the temperature logically would have the opposite effect. This is going to decrease the rate of the reaction. Again, when you lower the temperature, fewer particles are now going to have the energy to collide and react and make it over that activation energy barrier.